So again, a pleasure to introduce Professor P.P. Vaidyanathan. Already sang all the praises about him, all the multiple awards he has won. But there's one small connection that P.P. and I have. That's the P. The P stands for Perinkulam. It's a small village in Kerala where we were both born, but then kind of dispersed. So you can ask him more about Perinkulam and Palakkad.
Right. P.P. All right. Thank you. Okay. Can everyone hear me clearly? How about the last row? Can you hear me clearly? Good. Fantastic. That's great. All right. It's a great pleasure and honor to be here. And thank you for the invitation. And I don't have a picture of me and you guys together, but I put balloons. I put 6 balloons on each side. And I will not tell you why. You should know it. If you are here, you know why. Yeah. Great. Okay, you guys and I have known each other for 30 plus years. ICASPs and SPCOMs and isomers and whatnot. It has been such a wonderful journey being your friend, your guest. We all love you so much. The entire community loves you. So it's a great pleasure and honor. And this talk is different from the previous 2 talks in the sense I'm going to talk about one of his papers first. So you guys wanted me to go back in history and talk about a paper that's 30 years old, approximately. Then I said, Lucas, I have to read your paper again. He said, yes, you have to read it. So I read that paper again. So that's what I'm doing. This is the paper. Principal component filter banks, and the co-author is also here. Co-author, yeah, there he is. So very good. All right, good. So whenever I do this kind of talk about old papers, I insist on putting photos. Straight from IEEE, this is not image processed. This is the original as it appears, scanned by IEEE, not by me. All right. And here is all right, so you can see the half-toning in the image, right? Unprocessed half-tone image. All right. Okay, so before that, I also want to make, you guys talk about this and make connection to your work on filter banks. Okay, so I'll make connection to this work on filter bank. And background is an even older, okay, whenever I turn like this, can you still hear me? Because with Ali, it was, okay, so this mic seems to allow me to refer. Okay, okay. So I'll first briefly mention about this paper and then make the connection. So please bear with me because, like I said, I'm tracing back in history, so some of this is old stuff, but most of you would have forgotten, so that's okay. All right. So here is my picture. Again, this is even worse than the, because this is an even older. All right. Okay. So filter banks. There is analysis filters, decimators, quantization, and synthesis bank. Okay, that's the structure you all know. Those are called the subbanks in the middle, and at the output of the quantizer, there is compressed version, and then you create the uncompressed version by the synthesis bank, right? That's the standard structure. And normally we impose a statistical model on the input signal X of n there, stationary or wides and stationary typically. If there are M filters, cyclo wides and stationary with period M is typically done, okay? And usually what we do, one of the mathematical problems, there are many problems in filter banks. One of them is to minimize that reconstruction error in a mean square sense, okay? And it can be shown if you do it, then these standard textbook filters are not optimal filters if you want to minimize the mean square error. And the actual solution depends on the power spectrum. So one of the earliest papers to appear in the literature, one of the earliest, was the paper by Yogas, the paper that I showed you in the beginning, how you can optimize the filter bank according to power spectrum. It's a very beautiful paper. And if I remember right, the paper also got an award. It was one of his earliest papers. All right, so here is the filter bank again. And it's well known that it can be written in a polyphase form where the matrix EZ is more easy to use, so we call it EZ. And that polyphase matrix completely represents the analysis bank. Similarly, RZ represents the synthesis bank. Okay, and there is this so-called perfect reconstruction property, x hat is equal to x, if R times E is identity. And under that condition, if we put quantizers there, all the error is due to quantization. Okay, so now there is quantizers. If there is perfect reconstruction, only error is due to quantization. So minimizing the reconstruction error is equivalent to minimizing the error at the output due to quantizers. Okay, all right. So that is a theory. As a theoretician, this is what we did, and Hugo's paper also did that. But perceptual measures can also been used by many people to do this. Okay, and there is a unitary constraint imposed on the filters, and it is that this polyphase matrix RZ is unitary for all frequencies. This is called the para-unitary property. Okay, and under this condition, if we choose E to be the transpose conjugate of R, then there is perfect reconstruction. If the analysis filter is the transpose conjugate of synthesis filter, polyphase matrix, perfect reconstruction. Right? Under that condition, you put in the quantizers, then the only reconstruction error is due to quantizers filtered by the synthesis polyphase matrix. Okay, all right. So these are called orthonormal filter banks. Anytime there is para-unitary property imposed on the polyphase, it's called orthonormal filter banks. Okay, and I mentioned all these things, and this is already mentioned when there is perfect reconstruction. This is the perfect reconstruction property. Okay, all this is just a review of what I said before. So now enter this. Okay, so the question he asked, beautiful question. Okay, and of course, today, 30 years down the road, we know those things, but still, I am going back in history. Suppose we retain, instead of quantizing, forget about quantizers, I don't like quantizers. I want to retain only n of the m subbands and reconstruct. If I do this, then what is the optimum choice of filters? Meaning equivalently, what is the optimum EZ matrix? Okay. So if I want to keep a subset, and having kept the subset, the reconstruction error is minimized, right? And the answer depends on input statistics. These are called principal component filter banks, principal component reconstruction. Okay. And the concept was introduced in the paper by others. Okay, and this is the paper. And okay, so you give a vector notation to the input of EZ and output of EZ. Those are assumed to be Weissenstein stationary, which will be the case if the input x of n is either Weissenstein stationary, that scalar input is either Weissenstein stationary or cyclo-Weissenstein stationary. Okay, and the power spectrum of Y has this expression where E is that unitary matrix in the atomic case. Okay, for each frequency by frequency, we can choose this E to diagonalize this matrix because SXX is the power spectrum, therefore it's admission, positive, semi-definite, and whatnot, right? So you can diagonalize this matrix frequency by frequency, not very practical, but it's doable, right? That gives the best para-unitary filter bank. This is the PCFP solution. Theoretically, the optimum filter bank on paper is the one that diagonalizes frequency by frequency. With a rational set of filters, you cannot achieve it, but in principle, you can do it, right? Theoretically. All right. Okay, so what this means, the equation is right on the top, the diagonalizing equation. If you write the analysis filters H of Z, all these filters, H1, H2, H3, in vector notation, the fact that this E diagonalizes it means that every analysis filter is related to an eigenvector of that power spectrum. This SXX, that power spectrum SXX, take an eigenvector of that. That eigenvector relates, the kth eigenvector determines the kth analysis filter. That's the meaning of this, right? So every filter is in some sense an eigenfilter, in some sense, okay? In that sense, in the sense that's written there, right? So each filter comes from an eigenvector of this power spectrum. Okay, and let's see. So think of it like a KLT. The traditional KLT also diagonalizes the covariance matrix. Instead of covariance matrix, it's the power spectrum, which is the function of frequency. That's the only difference, all right? This may not be rational in the sense the filters may be rational filters, so we have to approximate them to realize. I'll show you an example. And when the input scalar X7 itself turns out to be Weissenstein stationary, the filter responses are piecewise constant. So I'll show you. These are examples straight from Ulysses' paper. Again, taken straight from the paper, no image processing on the plots. Plots as they originally appear, okay? All right. And there were many other results in that paper, which I am not talking about. connection to optimal wavelets, they talk about it, connection to continuous time, PC kernels, and deterministic case and White-Stationary case. There's a lot of details in the same paper towards it. Okay, you guys also said talk about connection to your work, and then I will stop. Okay, not quite. Okay, all right. So in my work in those days, I put quantizers. Instead of keeping n out of m subbands, I put quantizers and appropriate high bit rate models and whatnot, and quantizers with varying bits instead of dropping subbands. And we optimized bit allocation across the subbands. How many bits we allocate to the different subbands, we optimize that, and also optimize the analysis filters simultaneously. So this is like a joint optimization. Nothing is compromised, joint optimization. It can be shown that the joint optimization nicely decouples into optimizing the bit allocation and optimizing the filters. Okay, that can be shown. So we did this and minimize the reconstruction error by doing that, right? And we did this and we found under that unitary constraint that the solution we got is also the principal component. So the solution for the problem of optimizing bit allocation and the filters jointly is also the principal component filter banks that Jurgis added in this paper. So I didn't know it when I wrote this paper. Later on, Jurgis and I talked, and I realized that I'm getting the solution he got for a slightly different part. So that was quite nice to know. All right, so that's that paper. Okay, so these are examples straight from my paper of those optimum filters. That is the filter H0, H1, H2, H3, and so forth. Okay. No, the first one is power spectrum. Second one is a couple of filters. Out of the 4 filters in my example, there are 2 more filters I'm not sure. Okay. All right. These filters happen to be so-called compaction filters. Jurgis also mentioned compaction filters in his paper. Okay, what a compaction filter, I'll just define it briefly, is that given the input power spectrum, find the filter that maximizes the output energy subject to a Nyquist constraint. The filter magnitude squared should be Nyquist. That means if I plot the order correlation of the impulse response, which is the impulse response of the magnitude square, that should have the Nyquist property. Under that Nyquist property, if you maximize output energy, that is called the energy compaction filter. And this can be traced back a little bit. Mike Unser did that a little bit before us, and Jurgis and Satsanis, and had a number of papers to follow. Okay, good. So that's all I want to say about this one. Now, I am not allowed to talk about other papers, but I briefly mention, don't worry, I will not show any, I will not talk about it, I'll just mention this. Don't worry, I mention this because I love these papers. Okay, there is a 2-part paper, this is part 1, part 2. In those days, my students and I have read it so 20, 30 years ago, whichever you can figure it out. Beautifully written, wonderful papers, and much better pictures. And here are the co-authors, and they are all looking happy, and I have not seen Sergio. I didn't see him yesterday, maybe he's here today because I saw his name in the program somewhere. So hopefully he's somewhere in the audience. Okay, so this paper, again, on filter bank precoders and equalizers, set us also thinking in the direction, and I had a PhD student who followed it up. Especially part 2 of this paper is on channel identification blind equalization. That was really beautiful, inserting zeros in the time domain, or you can do it like a cyclic prefix in the frequency domain. That led to a number of ways of doing blind identification, and this student especially benefited. This student, his PhD thesis was inspired by this paper by Anna and etc. Okay, so thank you again for that inspiration. This was wonderful. And I mentioned this paper. Again, you already know that I keep the promise. I'm not talking about the things. I'm not showing the equations. Okay? Why I put this up is because this is so impressive. Look, at this point, Jurgis is already a fellow of the IEEE, and he is writing single author papers. How many of us do that, right? We always download it to students, right? Here he is discovering the results, doing the simulations, writing all these papers. So I was, wow, that is good. So that's the only reason I put it. Okay, all right. And mentioning this for a specific reason, because some of my recent work, okay, connecting a little bit. This paper is about how to find estimate more DOAs than number of sensors. Right? If you have a ULA with 10 sensors, it can at most find 9 sources using second order statistics. Okay? So in the last 10-15 years, there is so much work on sparse arrays, which are not ULAs. Using sparse arrays, we can find many more sources than sensors. You can find order of n square sources, even using second order statistics. That's important, even using second order statistics. But these authors, Sanyogita and Urdas, showed.
She's here.
Oh, she is here? Oh, very good, good. Okay, there she is. Okay, hello. Yeah. So they show how many years ago? That many years ago. Okay, 1993. You calculate. Okay, how many? 31. Okay, okay. Right. Years ago, that you can find more sources than sensors, even with ULA, if higher order statistics is available, not second order statistics. So here is this paper. Today, yeah, there is lots of good stuff on sparse arrays which can find more DOAs, okay, nested array, co-primary, all those things, right? But this one shows even ULA can do it if higher. So this wisdom, that you can find more sources than sensors even with ULA, if you have higher order statistics, we owe it to this. All right, and again, as promised, I always put pictures, all right, straight from the paper, not recent pictures. And now I'm going to give you the good news. You know what the good news is? Talk is over. All right, and once again, putting up the balloons and many, many best wishes, and we all love you. Thanks.
We can have questions only from non-authors of all the papers. So she is very good.
I thought the authors can quiz him, you know.
All the
Right, right. Therefore, feel free to ask.
Carry up for it, right? So,
No. Feel free to ask difficult questions because all authors said, I want to answer those questions. I'm going to direct it to you guys and Anna, and Sergio, and Sanyogita. Any easy questions you can ask. Oh, I can? I thought I'm not allowed, am I?
sure.
I won't because I have to read the paper again to be qualified.
We don't remember that paper. 30 years ago.
Very good. Looks like there are no questions.
I
Correct?
think Yargo had a comment.
Oh, yeah.
You kind of started to say something, yeah?
I guess among the people that contributed to the multi-channel higher order is the session chair, Anathan Swami.
Good. Good. I am proud that they are.
That's right, yeah. It's a small story about Yargo, right? I mean, 1,000 papers or whatever. Back to the end of a grad school days in USA, so good coffee was very, very rare. And the Starbucks opened a chain, and we said, we should go get a franchise. Story would be different, but at that time, the whole company owned stores, so they wouldn't let us open a store. Otherwise, Yargo would have been not here, but somewhere else.
Yeah.
He still drinks good coffee. Thank you, Kiki.
Okay,
Thank you, Peter.
Thank you. Thank you so much. Oh, that's the price.
Not a lot of things I can say.
I think it works. I got it home. My wife said, what is this?
I do that.